So let's derive the cake formulas, and cake comes from the acronym for constant acceleration kinematic equations. Note, these are not what will later in the course be referred to as the equations of motion. That is based upon Newton's second law, F equals ma. But these are constant acceleration equations. So we start out with acceleration. If acceleration is constant, then average acceleration is equal to the instantaneous acceleration. So acceleration is the same at any point, and average acceleration is the change in velocity over the change in time. Let us assume for the sake of this that the initial time is 0, so t initial equals 0 seconds. In other words, we start the clock at the beginning of the problem. And so this delta t, which is typically t final minus t initial, just becomes t final. And since I'm only dealing with one time, I'm just going to call it t. And so my acceleration is equal to final velocity minus initial velocity divided by time, multiply both sides by time, and I get acceleration times time is equal to final velocity minus initial velocity. We are dealing with vectors here, so the vector symbols are critical. And then I'm going to add vi to both sides. And so what I end up with is vf equals vi plus acceleration times time. That's when I add this over. And then I just flip the sides of the equation. And so that is the first cake formula. Now, this is not like Newton's laws, where Newton's first law is set. Every textbook always says Newton's law is the same. This just happens to be the first one that I'm deriving. It's typically also the first one that textbooks derive, but it's not ordered in any particular method. So that is the first of the cake formulas right there. Sometimes other variations of this, you'll just see V is equal to VI plus AT. Another variation, V equals VO plus AT. And I might have this in another video, but I for initial or O for original or 0 for when time is 0. I will use these interchangeably. Sometimes I'll write the equation, and then the next equation I'll flip over to the other symbols. So just recognize those mean the same thing unless otherwise defined. All right, so let's go for the next one. I know that average velocity is the change in position over the change in time, or we could just say displacement divided by time. Same argument as over there for the time. And so average, well, if velocity is average, if I have a velocity versus time graph here, if acceleration is constant, then the slope is constant. Acceleration is slope of velocity versus time. That is in another video, whether it's before or after this one, I'm not sure at the moment. And so if velocity is constant, so the average velocity, well, if that's a straight line, the average is just smack dab in the middle. That's going to be the average. So V average is just the initial velocity plus the final velocity divided by 2. It's just the average of those two numbers right there. This is your initial velocity, and that's your final velocity. And so we have VI plus VF divided by 2 is equal to delta x times time. And so therefore delta x, or the displacement, is equal to VI plus VF over 2 times time. That is the second one we're deriving right there. We also can drop the F here or put a 0 or an O in for I, and similar to the variations from up there. To get the next one, what I'm going to do is I'm going to take this equation right here and plug it in for VF. So I have my displacement is equal to VI plus VF, just rewriting what I just did, times time. And this is equal to VI plus, well, from the first equation we derived, plus AT over 2 times time. Let's go ahead and combine like terms here. So this is 2VI plus AT divided by 2 times time. And then distribute the 2, so this becomes VI plus 1/2 AT times T, which is VIT plus 1/2 AT squared. And that's, again, equal to the displacement. So that is the third one I'm deriving. And for the next one, we have to bring into this idea of dot products. So dot products care about it's a method of multiplying vectors. So if that's A and B with some angle in between them, then a multiplication using a dot product is I'm multiplying the parts that are parallel to each other. This is the part of A that is parallel to B, and this is the part of A that's perpendicular to B. So I'm going to multiply this part times B. In other words, A cosine of theta times B. You're multiplying magnitudes, so you get AB cosine theta. Now, what is important for this particular thing here is that notice that if I flip the order around, B dot A, well, I'm multiplying the part of B that's in the direction of A, so let's, again, try to draw them down there. And I would break B up into its components. I have a component going this way, a component going that way. These are perpendicular. This is the part of B that's in the direction of A. In other words, if that angle there is theta, this is B times the cosine of theta. So that's B, and this is A right there. So what we end up with here is B cosine theta times A, which is just AB cosine theta. So the commutative property of multiplication holds for dot products. It will not hold for cross products, but it does hold for dot products. So what I'm going to do is I'm going to take two equations here. I have my acceleration, which is VF minus VI over time. And then I'm going to take my displacement equation, which is VF plus VI divided by 2 times time. Now notice that is slightly switched from what I did right here, but commutative property of addition holds here, so I just flipped VI and VF. And I'm going to do multiply. I'm going to multiply those together, multiply those together. So this is A dot delta X. And on the other side, VF minus VI over T, dot product, VF plus VI over 2 times time. Now, the scalars here times the scalar, and that's just going to cancel out. The 2, I'm going to just multiply both sides by 2. And what I'm left with is 2A dot delta X. And then I'm left with VF minus VI dot VF plus VI. So just rewriting what I had, delta X equals VF minus VI dot product VF plus VI. And I'm going to FOIL here. So the typical classic first, outer, inner, last. And so this is equal to VF dot VF. And then those plus VF dot VI. Now these minus VI dot VF. And then last minus VI dot VI. Well, these right here, because remember the commutative property holds, so it doesn't matter the order in which I do it, these are equal to the same thing. Whatever VF and VI are, that these are the same, and so those will cancel out. And so now I have a vector dot product with itself. So if I have A dot A, well, it's just going to be the magnitude of one times the magnitude of the other times the cosine of the angle between them. Well, any vector has a 0-degree angle with itself. That's equal to 1, and so this is just equal to the magnitude squared. And so I end up with 2A dot delta X is equal to VF squared minus VI squared. If I add VI to the both sides and then flip the order of my equations, I have VF squared equals VI squared plus 2A dot delta X. And that is the fourth cake formula. There is a fifth one, which sometimes textbooks use. I tend not to do it, but there is a fifth one. And the fifth one is, if we come back over here and solve for VI and then plug into here, then you get an equation that looks very similar to the third one we derived, but it's a little bit different. I think your textbook might have it. I just don't remember. But the four big cake formulas we have, recapturing it here, VF equals VI plus AT. VF squared equals VI squared plus 2A dot delta X. Do notice that the vector symbol is gone at this point. This does produce a scalar product. A dot product is a scalar product. as in if you look at the review video on those, there is one specifically on dot products. So I have two which start out with VF, just one happens to be a VF squared, and this is also a scalar. And then we have two displacement ones, delta x is equal to VIT plus 1/2 AT squared, and delta x is equal to VI plus VF over 2 times time. And again, variations that you might have is VI and VO, VF and just plain V, and delta T and T. Some textbooks put in delta T, some don't. This is more of a universal non-calculus-based derivation. And those are the cake formulas right there. Constant acceleration kinematic equations. Later on in the course, you'll have cake formulas, which are the angular constant acceleration kinematic equations, or sometimes I'll write it as in constant angular acceleration kinematic equations, so CAAKE. There's an extra A in there. And so there it is.